gas law stoichiometry. So this is going to be the same as any other stoichiometry. We're going to convert to moles so that once we're in moles, we can use the balanced chemical equation to convert from the moles of the thing that we know to the moles of the thing that the question is asking about, using the mole ratio in the balanced chemical equation. But we have to be in moles in order to use that ratio, though we'll see a shortcut later. And then often the question is not asking for how many moles of something it is, it's asking for some other units, say mass or maybe volume or something like that. And so then our last step is essentially going to be convert to whatever unit it is looking for. It's the same process for all stoichiometry, but the ideal gas law is the way that we're going to get to moles in the beginning if we're starting off with a gas, or at the end if it's asking for something about a gas, say its volume, then we're going to use the ideal gas law to do that. So essentially, and this will be under any conditions, not just STP. If it happens to be under STP, you can use that ratio Avogadro thought about anyways, in terms of 1 mole at STP having a constant volume, and we know that to be 22.4 liters. But the ideal gas law will factor in any conditions, so it'll always work. So we know a number of ways to get to or from moles, which is what we're doing at the beginning, at the end of a stoichiometry question. We know from particles, if you want to go from particles to moles or moles to particles, it's going to involve the ratio of 1 mole having 6.022 times 10 to the 23 particles in it. And if you use that as a conversion factor, just use it in the way that the units work the way that you want them to work. If we're given a mass, then we know, pick up the periodic table, and you're going to be using the molar mass of that substance to get to moles, or if you had moles, to get to mass, depending on how you use it. With solutions, we know that often we're given a volume or something like that, and we can use the concentration, which is essentially the ratio of how many moles there are per liter for that particular solution. Now we're dealing with gases, and so to get to moles for gases, we are using PV equals nRT. This will get us from certain conditions, maybe the volume of gas under certain conditions, to moles, or from moles to volume under certain conditions. So, for example, let's try this one out. So, nitrogen and hydrogen gas, both of them gases, react to form ammonia, also a gas, under standard conditions. So, if 1 liter of nitrogen reacts with excess hydrogen, we don't have to worry about doing any limiting reactant for this question. How many liters of ammonia gas are produced given these conditions? And anytime you're dealing with a gas, you have to know the conditions that it's under, because otherwise, if the temperature or pressure changes, the volume of the gas is going to change as well. So you need to know under what conditions is that gas under. So this is under SATP, or standard ambient temperature and pressure. We know we're starting off with 1 liter. Being as this is a stoichiometry question, we have to have a balanced chemical equation to know what the relationship is between the nitrogen and the ammonia. And we know molar ratio is a 1:2 ratio for nitrogen to ammonia. We have 1 liter of nitrogen, so if we want to use that 1:2 ratio, we can convert to moles using PV equals nRT. We're going to first convert to moles, and then convert from moles of nitrogen over to moles of ammonia, and then we can find liters from there. So we can solve for the number of moles by rearranging the equation, plug in the values that we have. So we have our 1 liter here. That's going to be going in for volume. Our pressure, remember this is SATP, so standard ambient temperature and pressure. So the pressure will be 100 kPa. Temperature is 298, because it's 25 degrees Celsius over to Kelvin. And R is 8.314. And don't forget the units, kilopascal liters per mole Kelvin on R, so that when you do the calculation, you can cancel the units out. So kilopascals cancels out, liters cancels out, Kelvin cancels out, and you end up with 1 over moles on the bottom. So 1 over moles. We're dividing by moles, which is the same thing as having moles. So there are 0.0404 moles of nitrogen gas. Now we can apply this 1:2 ratio, and so let's write that out as a conversion factor. Moles of nitrogen will cancel out, and we're using the 1:2 ratio to get to moles of ammonia, and we would then have 0.0808 moles of ammonia. That's fine, but they're asking for how many liters of ammonia. So now we've got to take this moles and convert to liters. Since it's a gas, we can use PV equals nRT. In this case, we have moles, we're looking for liters. So rearrange for V, plug in your numbers. We're taking our moles, plug it in here. Same R value as always, that's why it's a constant. This is conditions of SATP, they have not changed, so we're still using 298 Kelvin and 100 kPa, and the volume works out to be 2 liters of ammonia. Therefore, 2 liters of ammonia are produced. Now, if you're not doing this blindly and you're actually thinking about what you're doing as you do it, you will have seen the shortcut by now. And this shortcut is going to work for any gases, any gas-to-gas stoichiometry question where you don't have the conditions changing. And if you think about it, here we took our 1 liter, we divided by 298, we divided by 8.314, and we multiplied by 100. We applied the mole ratio, and then we multiplied by 8.314, we multiplied by 298, and we divided by 100 kPa. So if you think about it, we essentially could eliminate mathematically this whole step here and this whole step here, and we would get the same answer. We just really need to factor in the mole ratio. And that should make sense, because here's the same question. Let's take the shortcut. Since this is a gas, since this is a gas, moles are proportional to volume, as Avogadro was saying. And so since it is an ideal gas, or pretty close to an ideal gas, it is a gas, the number of moles will vary proportionally to the volume, which means that the volume ratio will follow the mole ratio. So essentially, unlike with any other state, you have to get to moles before you can use the mole ratio. With gases, because moles and volume are proportional, you can apply the mole ratio directly to the volume. You can't do that with solids, you can't do that with liquids, but you can do that with gases. So as long as we are starting off with a gas and ending with a gas, it makes the work really, really easy. If we have nitrogen gas and we go to ammonia gas, we can see that the mole ratio is a 1:2 ratio. And normally we would have to convert to moles to use that ratio. But since these are gases, we can skip all of that work, and we can apply volume directly to that 1:2 ratio. So essentially we just take our volume of nitrogen, we apply a mole ratio to it, because that's what Avogadro showed us we could do with Avogadro's gas law. The moles and the volume for gases only are proportional. So the mole ratio applies to volume, as long as it's gases and as long as the conditions don't change. Otherwise you have to factor in a combined gas law type extension. So 1 liter would become 2 liters because it is a gas. Make sure you only apply this shortcut with gases when conditions are not changing. Therefore, 2 liters of ammonia are produced. If the conditions change, if we were starting with a solid or ending with a solid or starting with a solution or something like that, you cannot take this shortcut. This only works for gas to gas stoichiometry under, doesn't matter what the conditions are, as long as they don't change.